Topic 2 of our Module 3 is helical springs. Enclosed coiled helical springs, composed of a wire of round rod of diameter d wound into a helix of mean radius r with n number of turns, is subjected to an axial load P, produces the following stresses and elongation. The maximum shearing stress is the sum of direct shearing stress P over area and the torsional shearing stress TR over J, with T is equal to P times R. So in here, we have the maximum shearing stress is equal to the direct shearing stress and the torsional shearing stress. Now we have the direct shearing stress is force over area, and the torsional shearing stress is dr over J. Now for the cross-sectional area to be considered, since if this is the force, yung shearing area natin is this, no? So yung cross-sectional area ng spring, and that is considered as a circle, no? So circular yung cross-sectional area. So we have here P over pi diameter square over 4, plus we have the TR over J, and from our previous topic, if we are going to derive this, we would have the formula 16t over pi d cube. But in here, it says that the torsion is equal to PR. We have here 16. The T would be PR over pi d cube. So simplifying this, and we would have the maximum shearing stress is equal to 4p over pi d square plus 16 PR over pi d cube. And if we are going to take the common denominator, so we have here pi d cube, so this would give us 4p multiplied by the diameter plus 16 PR. If we are going to factor out the 16 PR over pi d cube, then for the first term here, so we would have here 4 divided 16 is 1/4, so that's over 4, and the P would be factored out, and we have here the diameter. We factored out the denominator, and this is it. And we factored out R, but we didn't have R in this term, so we have over R here. Plus, as you can see here, we factored out this, and this is equal to 1. And simplifying further, and we will have 16 PR over pi d cube multiplied by 1 plus d over 4R. And this formula neglects the curvature of the spring, and this is used for light spring where the ratio of d over 4R is small. For heavy spring and considering the curvature of the spring, the Wahl's formula, which is more precise, is used, and it is given by the maximum shearing stress is equal to 16 PR over pi d cube multiplied by 4m minus 1 over 4m minus 4 plus 0.615 over m, where m is the spring index and the factor 4m minus 1 over 4m minus 4. This is referred to as the wall factor. So, what is the value of spring index M? Spring index M is the ratio between the diameter, that diameter D is this, and the lowercase diameter is diameter of the spring. So we have here this diameter over the diameter of the spring. For the deformation, we have the formula. Deformation is 64 PR cubed N over GD to the fourth, wherein the P is the applied load, the R here is this radius, and the N is the number of turns, and G is the modulus of rigidity, and this D here is the diameter of the wire. So we notice that the deformation is directly proportional to the applied load P. So the ratio of P and the deformation is called the spring constant. So the spring constant, which is denoted as K, is the ratio of the load and the deformation. And we have here, since the deformation is equal to 64 P R cubed N over GD to the fourth, then we have the spring constant equal to, cancel out, the P would be cancelled out, and take the reciprocal. So we have here GD to the fourth over 64 R cubed N. And the unit of the spring constant is in Newton per mm. Topic 2.1, we have the spring in series. So for two or more springs with the spring laid in series, the resulting spring constant K is given by the equation 1 over K is equal to the sum of 1 over K per spring. So if you have a total of 5 springs here, then that would reach up to 1 over K to the fifth, or that's 1 over Kn. So where K1 and K2 are the spring constants for different springs. Topic 2.2, spring in parallel. For two or more springs in parallel, the resulting spring constant is just the sum of the spring constants. So with K1, K2 up to the Kn are the spring constants for different springs.